Friends, welcome back to Electriverse, where every spark tells a story. If you have seen part 1 of the VSD series, then you will now have a strong idea of the basic structure of VSD, PWM, synchronous speed, DC bus capacitor, faults, and basic troubleshooting. In part 2, we are going to enter a zone inside the VSD where actual engineering begins. Protection settings, carrier frequency, harmonics, real case studies, and interview level thinking. These are the topics that people often only know by name, but the true meaning and impact on the plant are not clear. Today, we will not just give headlines. We will understand in detail why VSD protection is needed, how it works, what dangers incorrect settings pose, and how the right settings build confidence. Let's start. First, understand a simple thought. VSD is not a normal small electronic device. It is a powerful power electronic system that chops, shapes, and filters high voltage to supply the motor. Now, if such a device, which contains IGBT, DC bus capacitor, high frequency switching, and complex software, is operated without protection, what will be the result? The motor may overheat, cables may burn, there could be a fire risk inside the panel, and the entire plant may experience an outage. That is why VSDs have multiple layers of protection. This protection not only protects the drive but also safeguards the motor, cables, upstream breaker, transformer, and plant personnel. If you ignore the protection, the drive may appear to operate in the short term, but failure is almost guaranteed in the long term. We can broadly understand VSD protection in two levels. The first level is electrical protection. This includes items like overcurrent, overvoltage, undervoltage, short circuit, ground fault, phase loss, and phase imbalance. All these protections take immediate action when current and voltage become abnormal. The second level is thermal and mechanical protection. This includes motor overload, motor thermal model, drive, heat sink temperature, fan failure, ambient temperature, and stall prevention features. These protect the system from thermal and mechanical stress. Once you understand these two categories, every fault code starts fitting into one, making troubleshooting easier. Now let's understand overcurrent protection in detail. Overcurrent simply means that the current flowing through the motor exceeds its rated current. But the reason is not always the same. Often there is a sudden increase in load on the motor, such as the impeller of a pump jamming, material jamming on a conveyor, fan blades, choking, or the coupling jamming. In this situation, the motor's torque demand increases, and according to the torque formula, the current also increases. The VSD continuously monitors the current. If the current exceeds a certain threshold, the drive first applies a limit, and if the current still cannot be controlled, it trips. In this setting, there is a parameter called current limit, and another parameter that determines how long the drive will tolerate an overload situation. If you set the current limit too high, the motor may overload. If you set it too low, the drive will trip unnecessarily. Therefore, engineering judgment is very important here. If I'm asked in an interview what I would check in case of an overcurrent fault, I would need to consider both the electrical and mechanical sides. Overvoltage protection mostly triggers around the DC bus. You heard in part 1 that the DC bus capacitor smooths the DC. Now think, when the motor is running at high speed and you suddenly give a stop command to the drive, the motor continues to spin due to inertial load. At this stage, it starts behaving like a generator, and energy is pushed back onto the VSD's DC bus. This causes the DC bus voltage to increase. If this voltage exceeds the safe limit, the drive trips with an overvoltage fault. This is the drive's self-protection. The engineering solution to this problem is a braking chopper and braking resistor, or adjusting the deceleration time. The braking resistor converts extra energy into heat and keeps the DC bus within safe limits. If in an interview someone says, overvoltage fault occurred during deceleration, your answer should not be just reset. You should discuss both the braking system and the deceleration ramp. Undervoltage protection is equally important. A VSD cannot operate properly below a certain minimum. DC bus level, because its control circuits, gate drive circuits, and protection logic all require a stable supply. If the input AC supply dips, or upstream breaker contacts are loose, or cable joints are weak, an undervoltage condition can occur at the VSD input. In this condition, the drive will trip because IGBT switching is not stable at low voltage, and the risk of unexpected behavior increases. The root cause of this fault is not always inside the drive. Sometimes it is an indicator of upstream system health. Therefore, when an undervoltage fault occurs, you should check the entire path from the panel to the transformer. Verify voltage drops, cable heating, loose connections, and overloading. Now let's talk about motor overload protection. This protection does not make decisions solely based on current. Rather, it approximates the thermal behavior of the motor. Inside the VSD, there is a motor thermal model. This model estimates an internal temperature by considering the motor's rated current, service factor, cooling pattern, and duty cycle. If the current exceeds the rated current slightly, but only for a short period, the model will tolerate it. However, if the current remains high continuously, the thermal model will indicate the winding is overheating and tripping is necessary. Therefore, motor overload trips should not be taken lightly. This means that your load is demanding more than the motor's design capacity. You may need to reduce the load, upgrade the motor rating, or optimize the process. This is also a typical interview question. Motor overload occurs. What will you do? You will check not only reset, but also the process and motor selection. Now let's move on to a concept that people often skip: carrier frequency. In part 1, you heard about the PWM concept. The frequency at which the IGBT switches to generate PWM is called the carrier frequency. In simple terms, the carrier frequency determines how many times per second the drive switches on and off. As the carrier frequency increases, the PWM waveform becomes smoother. The current waveform on the motor appears cleaner, but switching losses also increase. Switching loss means heat. So one advantage of a high carrier frequency is the motor runs smoothly and noise is reduced. But there is a negative point. Both the drive and motor generate more heat. You need to understand the carrier frequency, not from the theoretical formula, but from the behavior of the real plant. At low carrier frequency, the motor will produce a slight, audible humming sound. Some people may find this sound objectionable at times, but from an electrical perspective, low carrier frequency has benefits: reduced switching losses, less heat, and better drive life. At high carrier frequency, the motor can be almost silent, especially under light loads. However, here IGBT switching occurs so frequently that more heat starts to generate. If the panel ventilation is weak, or if the motor is in an already heated environment, then long-term failure risk can increase with high carrier frequency. Therefore, the correct approach is to tune the carrier frequency according to the application. If noise is critical, a slightly higher setting should be chosen. If reliability and long life are priorities, a moderate value should be selected. Let's understand these harmonics with a reality check. It is written in textbooks. Harmonics are higher frequency components on top of the fundamental waveform. But what is their actual effect in a plant? Due to harmonics, extra I² R losses occur in cables, meaning more heat is generated. Core losses and copper losses increase in transformers, causing the transformer to heat up. Breakers, contactors, and relays, whose contacts are rated according to sine wave, can behave unpredictably on a distorted wave. Sensitive equipment like control systems, instruments, and communication devices may have their reference voltage disturbed. This means harmonics are not just a theoretical problem. They directly impact plant reliability, energy bills, equipment lifespan, and process stability. Therefore, avoiding the topic of harmonics with VSDs is a dangerous approach. Now let's talk about solutions. The most common ways to reduce harmonics are line reactors, passive filters, active filters, 12-pulse and 18-pulse rectifiers. A line reactor is basically an inductor that is installed on the drive input. It slows down the rise and fall of current, which reduces distortion to some extent. It is simple, economical, but provides moderate level benefits. Passive harmonic filters target specific harmonic orders. These are tuned circuits that absorb certain particular frequencies. They are useful, but the design must be correct. Otherwise, system resonance can also occur. Active harmonic filters are quite advanced. They analyze the load current in real time and inject opposite harmonic currents, cancelling out the net harmonics. They are more costly, but provide a powerful solution for large plants. 12 pulse and 18 pulse. VSD rectifiers are inherently harmonic friendly because their rectifier stage uses multiple phase shifts and harmonics cancel out. They are mostly used in high power drives where harmonic limits are strict. Let's now look at a real field case study. In a plant, overvoltage faults kept occurring whenever the operator gave a stop command to the drive. The maintenance team first installed a braking resistor, but the fault still occurred occasionally. When analyzed in detail, it was found that the deceleration time was set very low. The motor was driving a heavy inertial load, and the drive was trying to stop it quickly. As a result, more energy was returning to the DC bus in generator mode, which momentarily exceeded the capacity of the braking resistor. The engineering solution was simple. The deceleration time was increased slightly, the braking resistor selection was verified, and the system became stable. This teaches us that adding hardware alone is not a solution. Parameters also need to be tuned logically. The second case study was of a fan application. The operator was complaining that at high speed, the motor vibration and humming increased. Everyone first checked the mechanical alignment, bearing, foundation, and coupling. The mechanical side was found to be almost okay. Then someone checked the carrier frequency setting. It was found that the carrier frequency on the drive was set to a value close to the mechanical resonance frequency. This caused a combined mechanical plus electrical resonance in the system. When the carrier frequency was slightly adjusted, the vibration significantly reduced without changing any mechanical components. This example shows that VSD parameters not only impact electrical aspects but also influence mechanical behavior. In the third case, the drive was giving random ground faults. Many times it tripped at start, sometimes during load change, sometimes even without load. The team first conducted a motor insulation test, checked continuity and insulation in the cable. Everything was fine. Still, the fault recurred. Finally, an experienced engineer examined the panel grounding layout. It was found that the earthing conductor connection was loose and the drive's reference was not stable. Because of this, the sensing circuits were sometimes detecting false ground faults. Simply cleaning and tightening the earthing joint resolved all the random faults. The clear learning here is, not every fault has an answer in the drive's menu. Sometimes, basic grounding and bonding are the biggest culprits. Think about it. If you're asked in an interview, what is the role of protection in VSD? What impact does carrier frequency have on motor and drive? How do harmonics affect the plant? What can you learn from field case studies? If you listen attentively to both part 1 and part 2, you will be able to answer not just with definitions, but also with real-life examples. This is the difference between an average candidate and a true Electriverse engineer. Friends, this was part 2 of the VSD series. In this part, we explained in detail the protection logic, carrier frequency behavior, harmonics impact, and some real field case studies. In the upcoming parts, we will cover more advanced topics such as parameter tuning, motor auto tuning, VSD, and soft starter comparison, earthing schemes, shielded cable practices, and practical checklist for commissioning. Therefore, if you find this series valuable, be sure to follow the entire VSD series till the end. If you liked this video, please like it, write in the comments which VSD topic you want next, and share it so that other engineers also get help. And most importantly, subscribe to the channel so that the effort we put into Electriverse content directly reaches you and takes your career to the next level. Thank you so much for watching Electriverse, where every spark tells a story. Stay charged, stay safe, stay happy.